Hello, my name is Abrar, and I'll be presenting about how closest pair queries and minimum weight queries are equivalent for squares, which is my submission to CCCG 2020 with Michiel Smid. So let S be a set of n weighted points in the plane, and let R be an axis parallel rectangle query region. The range closest pair problem asks us to report the closest pair of points in R intersect S, whereas the range minimum weight problem asks us to report the minimum weight of any point in the intersection of R and S. So here are some of the best known results for the range closest pair problem. We can achieve a query time of big O of log squared of n using a data structure of size big O of n log squared n, and this result is due to Xue. And if R is a square, or more generally a fat rectangle, then we can achieve a query time of big O of log of n using a data structure of size big O of n log n, and this result is due to Bay and Smid. So here are the main results of our submission. We show that range closest pair problem and the range minimum weight problem are equivalent for squares. So Theorem 1 states that if there exists a data structure of size m of n that answers a range minimum weight query for any query square in q of n time, then there exists a data structure with big O of the same size and the same query time that answers a range closest pair query. And Theorem 2 is just the converse, which shows that range minimum weight queries reduce to range closest pair queries. So now I'll be going over the structure of the presentation. First we will cover Theorem 1, in particular answering what are so-called closest C of P queries and some other related queries, and then presenting a reduction from minimum weight queries to closest pair queries. And then I'll be covering Theorem 2, which is the reduction in the other direction from closest pair queries to minimum weight queries. So let S be a set of endpoints in the plane, and let C be an integer between 1 and n, and let P be any point in the plane. If the cardinality of the set, the northeast quadrant of P intersected with S, is greater than or equal to C, then closest C of P is the set of the C points in that intersection that are closest with respect to the Manhattan distance to P. And if this set has less than C points, then closest C of P is just the set itself. So here we have an example with C equal to 2, and here's our query point P. We can see that these are the points of S, which also line the northeast quadrant of P, and these two red points here that are highlighted are the closest 2 points to P, according to the Manhattan distance. Now we have the following theorem stating that if S is a set of n points in the plane and C is an integer between 1 and n, then there exists a data structure of size big O of C squared of n, such that for any query point P, the set closest C of P can be computed in big O of log n plus C time. Okay, so now I'll be explaining how to construct the closest C data structure using an example where C equals 2 and n equals 7. So first we take the 7 points of S, and we order them in the order in which a line of slope -1 passing from left to right across the plane would encounter them. So as you can see, this point number here, point 1 number here would be encountered first, and point 7 here would be encountered last. Then for each point in the plane, depending on their order, we extend two rays from them, one going horizontally to the left and one going vertically downwards, and we extend the rays until either they reach -infinity or until they encounter two other lines in the subdivision. So going through the first few iterations, 1, 2, 3, 1 through each 4, we see that as we extend this ray downwards from 4, first it passes through this horizontal line over here, and then it encounters this horizontal line and comes to a stop. And then we keep doing the same process with 5, 6, and 7, and finally we have this final subdivision over here. So now on this next slide, I've just expanded that final subdivision from the previous slide. And inside each cell, I'm displaying the closest C points of the top right vertex of that cell. So for example, if we look at this cell over here, this is the top right vertex of that cell. And if we can see that the points 3, 6, and 7 are all visible from the northeast quadrant of this vertex. And the two closest points to this vertex, according to the Manhattan distance, are 3 and 6. And therefore I associate that set with this cell. And now the query algorithm is as follows. Given a point, first locate the cell that it's in. So suppose the point is over here in this cell. Then I locate this cell using a point location algorithm. And then I simply report the set which is associated with that cell. So in this case, 3, 6. And the correctness of this query algorithm follows from the fact that the closest C points to the top right vertex of a cell is actually the same as the closest C points of any other vertex contained within that cell, any other point in that cell. Now let's see the size and query time requirements for this closest C data structure. So first, it can be shown that on each iteration, the total number of cells and edges increases by an amount that is proportional to C, and so the data structure has big O of Cn cells and edges. Having big O of Cn cells implies that big O of C squared n space is required for all the sets closest C of Z. And having big O of Cn edges implies that big O of Cn space is required for the point location data structure, and big O of log of Cn time is required for point location, which breaks down to big O of log n plus log C. And finally, reporting that set the closest C points takes big O of C time. And so putting all of this together, we get that the total space and query time requirements are big O of C squared n and big O of log n plus C respectively. Okay, now let's move on to some related queries. So here I have lemma 7, which says that if S is a set of n points in the plane and C is an integer between 1 and n, then there exists a data structure of size big O of C squared of n, which can perform the following query in big O of log n plus C time. Given a query point P, find the smallest square that has P as its bottom left corner and contains C points of S. So here we have an example where C is equal to 3, and we can see down here we have our query point P. So you can see that this red square over here is the smallest square which has P as its bottom left corner and which contains 3 points of S, highlighted here in red. So we can see that we can answer this query just by finding the C lowest points of this cone over here and finding the C leftmost points of this cone over here, and then combining those two sets, and among those two C points, just finding the C points which are closest to P according to the infinity norm distance. So here on this next slide, I've taken one of the two cones from the previous diagram on the previous slide, and I've shown here that finding the C lowest points in this cone corresponds directly to finding the C points in this transformed quadrant, which are closest to T of P according to the Manhattan distance. And therefore, queries of this type reduce exactly to queries of the closest C type that we've seen before. And so we can obtain a data structure with the same exact query time and space requirement as the closest C data structure. So now let's take a look at another related query. Lemma 8 states that if S is a set of n points in the plane and C is an integer between 0 and n minus 1, then there exists a data structure of size big O of C squared of n, C squared n, which can perform the following query in big O of log n plus C time. Given a query square R, decide whether the intersection of R and S has less than or equal to C points, and if so, report those points. So here we have an example where C is equal to 3, and we have two example query squares R. So we have this inner square over here and this outer black square over here. And to answer such a query, we can just appeal to the data structure from lemma 7 using a value of C equals 4 for that data structure to find the smallest square anchored at this bottom left point here, which contains 4 points of S, and we get that as this dashed red square over here, which as you can see contains 4 points of S, and it's the smallest possible such square. And now, for example, if this is our query square R, we see that since this square is contained within our dashed red square here, that means that it contains strictly less than 4 points, or less than or equal to 3 points of S, and therefore we can just report that fact and report those points which it contains. And otherwise, if our square contains the square that is returned by our query to lemma 7, then we know that it has at least 4 points, and therefore we can report the fact that it does not have less than or equal to C points. And so once again, it just reduces to having the same query time and space requirements as the previous two data structures, namely a size of big O of C squared n and a query time of big O log n plus C. So now finally we're ready to discuss how minimum weight queries can be used to answer closest pair queries. So from Bay and Smid's approach for range closest pair queries with squares, they use data structures for the following. First of all, deciding whether a query square contains at most c points of S for some fixed constant c. So as we have seen, queries like this can be done in big O of log n time, using big O of n space, using a data structure of the type of lemma 8. And secondly, computing the smallest square that has a query point as its bottom left corner and contains c prime points of S for some fixed constant c prime. And as we have seen, this can be done in big O of log of n time and big O of n space, using a data structure like the type of lemma 7. And finally, performing range minimum weight queries with squares. And therefore, if range minimum weight queries with squares can be performed using a time which is greater than log n and a space which is greater than n, then we can perform closest pair queries using those same exact time and space requirements. And now last but not least, let's look at reductions in the other direction, namely how to use closest pair queries to answer minimum weight queries. So in this diagram over here, every black point is a point of S, and as we can see, they're all weighted, with weights written above the points. And for each such point, we will add 2 dummy points, indicated here in red, such that the distance from a dummy point to its parent is proportional to the weight of its parent, and also these distances are scaled down in such a way that for any given dummy point, the closest point to it is always its parent point, and given any query square R which contains at least 2 points of S, so at least 2 black points, we are guaranteed that for every such point of S, we'll have at least one of its 2 dummy points contained within that square. So you can see, for example, here with this point, we have the right child point is also within the square, and for this point of S, its left child dummy point is also within the square. So then to answer a minimum weight query, we simply answer the closest pair query within that square, and then whatever the closest pair is, just find the parent point in that pair and report its weight. And thus we can answer minimum weight queries by answering closest pair queries. That concludes my presentation. Thank you for watching.